Good morning, students. Today we are starting our revision schedule, and the chapter we are taking is light. What is light? Light is a form of energy which produces a sensation of vision in our eyes. Light travels in a straight line, and whenever light falls on an opaque object, some of the light is absorbed by the object and rest of the light is reflected. That is called reflection of light. Whenever light encounters an opaque object into its path, it bounces back in the same medium, and that's called the reflection of light. There are certain laws of reflection, like if the surface is smooth, the rays of light striking the surface will be reflected in the same pattern. But if the surface is rough, the parallel beam of light will be reflected in different directions. The first one is called regular reflection, and the second one is called diffused or irregular reflection. If we are talking about reflection from a plane mirror, it follows two laws. First, the angle of incidence with the normal and the angle of reflected ray with the normal both are equal. So angle of incidence is always equal to the angle of reflection, and the incident ray, the reflected ray, and the normal all lie in the same plane. The mirror which we are using in everyday life is a plane mirror, but there are two other mirrors, a concave mirror and a convex mirror. A concave mirror is one in which the reflecting surface is on the concave side, on the inside, and the convex mirror is that in which the reflecting surface is on the outside. Take the case of spoon. Where we put the food, that is the concave side, and the reverse is the convex side. This diagram, quite frequently asked in your exams, is characteristics of image formed in a plane mirror, followed by the diagram. So take a plane mirror, an object. From the head of the object, take two rows, one normal to the mirror and one striking the mirror obliquely. The first ray will be reflected back. It will retrace its own path, and the second ray will follow the normal laws of reflection. When we produce both the rays behind the mirror, they appear to come from the same point behind the mirror, and this is where the virtual and erect image is formed. So image formed in the plane mirror is behind the mirror, at the same distance behind the mirror as the object is in front of it, and the image size is always equal to the object size, and the image is virtual, erect, and same size as the object. When we are talking about spherical mirrors, there's some terms used in the case of spherical mirrors. First is the pole, center of curvature, radius of curvature, principal axis, principal focus, focal length, and the aperture of the lens. First of all, keep in mind that spherical mirrors are a part of a big sphere. If the outer surface is reflecting, it will give us a convex mirror, and if the inner surface is reflecting, it will give us a concave mirror. The center of this sphere, of which the mirror is a part, is called the center of curvature. Distance between the center of curvature to any surface on the mirror is known as the radius of curvature. The central portion of this mirror, the mirror has a center. If we are looking it from the side, but if we look from the front, the mirror will appear as a circle. The center of that circle is called the pole. The line joining C and P is equal to the radius of curvature, and the geometrical center of CP, line CP, that is the radius of curvature, gives us the principal focus. So CP is the radius of curvature and FP is the focal length. And the diameter of the mirror which we are using, that diameter is known as the aperture of the mirror. There are certain laws which we follow while making the image in a spherical mirror. First of all, let's keep in mind certain points while making the ray diagrams for image formed in spherical mirrors. All the distances are measured from the pole. The pole is the original point or the origin. Just as in coordinate geometry, when we are making graphs, we take origin, which is 0, and from the origin we take all the distances either left or right. All the distances are measured from the pole. Distances measured in the towards the right side are taken as positive. Distances measured upwards, again taken as positive. Distances measured to the left and on the downward side, both are taken as negative, as just the same as we consider the graph. This is a concave mirror. In this, the focal length and the radius of curvature and the object distance all are measured towards the left side, so all will be taken as negative. In case of convex mirror, focus and center is on the right side, so the focal length and the center radius of curvature both will be taken as positive. But object is always placed on the left side, therefore object distance is always taken as negative. Now coming to the ray diagrams. A ray of light traveling parallel to the principal axis will pass through the focus after reflection from a concave mirror. On the contrary, if a ray of light is passing through focus and striking the mirror, then it will become parallel to the principal axis after reflection. Mostly these two laws are considered while making ray diagrams for the image formation in concave and convex mirrors. Now, first case in the concave mirrors is when the object is at infinity. Then the image is always formed at the focus. The size of the image is highly diminished. You can say point sized. And the image will be formed at the principal focus, and image will be real, inverted and highly diminished. Keep in mind that whenever the rays of light after refraction or reflection, when they meet actually, the image will be real and inverted. But if they appear to meet or they meet virtually, then the object image will be virtual and erect. Now second case, when the object moves slightly closer to the mirror, that is, the object is now placed at a distance which is more than the radius of curvature. That is, the object is beyond the center of curvature. Then the image formed will be between the focus and the center of curvature. Again, the reflected rays are actually meeting, so the image will be real, inverted, and as we see, diminished. That is, the image is slightly smaller than the object. Third case, when the object is placed at the center of curvature. In this case also, we will follow the same pattern and we would see that the image is formed also at C. The reflected rays are actually meeting, so we will say that image formed is real, inverted and the same size as the object, because the object is placed at C and image is also formed at C. Another case, object is now moving closer to the mirror. So the image will move further away. Now the object is placed between center of curvature and focus. Again, follow the same pattern. The reflected rays are actually meeting, so the image is real, inverted, and in this case, it is now enlarged. Now object moves at focus further towards the mirror. The image will move again away from mirror, and if the object is placed at focus, the image will be formed at infinity, again real, inverted, and highly diminished. Now the last case, that is, now object moves further closer to the mirror, more closer to the mirror. Now what happens? In this case, the image will be virtual and behind the mirror, and it will be virtual, erect, and enlarged. This is the case where we use this concave mirror as a shaving mirror. Concave mirror is used for several applications like a shaving mirror, a torchlight reflector used in the vehicle's headlamps. A dentist uses a concave mirror. It is used in a microscope, in telescopes, and solar furnaces. Now coming to convex mirrors. Convex mirrors have only two cases. First, when the object is at infinity. Second, when the object is between infinity and the pole of the mirror. In both the cases, the image formed will be behind the mirror, that is virtual, erect, and diminished. Convex mirrors are used as an observation mirror in big departmental stores or big halls, and also the busy intersections of road where while turning you are not able to see actually the vehicle. So these mirrors are installed there so that accidents do not happen, and also in the rear view mirrors of the vehicles. Now coming to the mirror formula. This is very helpful in attempting your numerical problems. F represents the focal length, V represents the image distance, and U represents the object distance. And the formula is 1 by F equals 1 by V plus 1 by U. The size of the image and object, they bear a ratio with each other, and that ratio is also borne by the image distance and the object distance. So size of image divided by size of object, that is HI upon HO, will bear the same ratio as the image distance to the object distance, but with a negative sign. Why? Because the real images are formed on the same side as the object is there. Now coming to refraction of light. What is refraction? Whenever light enters from one medium to another, which have different optical densities, then the light rays change their path, or the light rays bend slightly. That bending of light is known as refraction of light. So whenever a light ray is entering from a rare medium like air to a dense medium like water or glass, it will move slightly towards the normal. In this case, light is entering from air into glass. So when the incident ray strikes the boundary between the two media, then at that point, that is called the point of incidence, a normal is drawn perpendicular to the surface or the boundary. And the light, whenever it is coming from a optically rare medium to an optically dense medium, it will bend towards normal. And whenever light is traveling from a dense medium to a rare medium, then it will bend away from normal. Keep in mind, from denser to rarer, away from normal, and from rarer to denser towards normal. As in the case of reflection, refraction also follows two laws. That is, the first law, that is, the incident ray, the refracted ray, and the normal all lie in the same plane, and the sign of angle of incidence and the sign of angle of refraction bear a constant ratio for a given pair of media. Suppose we are talking air and glass, then whatever be the angle of incidence, there will be a corresponding angle of refraction, and the signs of both angle of incidence and the angle of refraction will always be a constant for air and glass. This is also known as Snell's law. Another method of calculating this is the speed of light in medium 1, that is, in our case it was air, and the speed of light in medium 2. These also bear the same ratio as this ratio. And this ratio or this ratio, both are same, and it is called the refractive index of the second medium with respect to the first. Like in our case, the refractive index will give us the ratio of speed of light in air and the speed of light in glass. Eyeglasses, spectacles, prisms, formation of rainbow, in all these phenomenon, refraction is involved. Now, refraction through a lens. First we did refraction through a glass slab. Now coming over to refraction through a prism. In the case of glass slab, the refracting surfaces were parallel to each other, but in case of prism, they are not parallel, they are inclined at a certain ratio to each other, and this angle is known as the angle of the prism. Incident ray strikes the surface at point of incidence. Perpendicular to this surface, a normal is drawn. So, light is entering from air into glass, so it will bend towards normal. Now, light goes to the other surface. Again, at this point of incidence, a normal is drawn. And whenever light is entering from glass to air, it will move away from normal. So, after suffering refraction 2 times, this ray of light emerges in this direction. Now, if the prism was not there, light would have gone in the original direction like this. But due to the presence of this prism, light is now emerging in this direction. So, this angle, that is the angle of the emergent ray to the original direction of light, is known as the angle of deviation. And incidence, emergence, deviation and angle of prism, they bear a certain relation with each other. A combination of prisms gives us lenses. If 2 prisms are joined base to base, inverted to each other, then the combination would give us a convex lens. If they are joined from tip to tip, then the combination would give us a concave lens. As you can see here, a convex lens converges a parallel beam of light, so it is converging, and a concave lens is diverging lens. Like the terms used in the case of spherical mirrors, the same terms are used in case of spherical lenses also. Like the diameter of the lens is called the aperture. But in case of mirrors, we had pole. Now, in case of lenses, we have optical center. It plays the same role as the pole in case of mirrors. The radius of curvature, that is the radius of that sphere from which the lens is carved out is called the radius of curvature. Principal axis, the line joining the center of curvatures which passing through the pole is called the principal axis. And focus is that point from which the parallel beam of light seem to converge or actually converges. Sign convention is same as in the case of lens mirrors. All distances are measured from optical center. Distances towards the right are positive, towards up positive, towards left negative, and downwards negative. Object is placed always on the left side, so u is always negative. In this case, the real image is formed on the right side. So, in case of mirrors, if the image is real, its distance will be positive, and if the image is virtual, its distance will be negative. Keep in mind and always remember that whenever in your question, either mirror or lens, if the term comes out to be positive, to be convex, then the focal length will be taken as positive. And if the lens or mirror comes out to be concave, then the focal length will be negative. So, if either the lens or the mirror is convex, f is positive, and if they are concave, f will be negative. Like in the case of spherical mirrors, there are cases of spherical lenses also, like when the object is placed at the infinity, the image is formed at the focus on the right side focus, and it will be real, inverted, and highly diminished. If the image moves closer, if the object moves closer to the lens, the image will move further. Now the object is placed beyond 2f. In case of mirror, it was C, but in case of lenses, it is f and 2f. Beyond 2f, the image will be formed between the focus and the 2f of the right side, and it will be real, inverted, and slightly diminished. Third case, when the object is placed at 2f on the left side, the image will be formed at 2f on the right side. Distances are same, so image size and object size will also be the same. So image will be real, inverted, and same size as the object. If we move the object further closer to the lens, the image moves further away. Now the object is placed between 2f and f on the left side. So image has moved beyond 2f on the right side, and it is now real, inverted, and magnified. Now the object moving closer to the lens comes to the focus. So image goes further away, and now in this case, when the object is placed at the focus, the image will be at infinity, real, inverted, and highly magnified. Now, if the object moves further closer to the lens, that is between f and the optical center, now the image will not be real anymore, it will be virtual, and it will be on the same side as the object is, that is on the left side, and it will be virtual, erect, and magnified. This is the case where this convex lens is used as a magnifying lens. These are the some devices or objects or items used in daily life which make use of the convex lens, like microscope, a camera lens, projector lens, flashlights, magnifying glass, and telescope. Coming to concave lenses. As we know that concave lens is a diverging lens, it will always form virtual and erect image. The object is placed at infinity. Image will be at the focus on the left side only, and it will be virtual, erect, and highly diminished. If the object moves anywhere between optical center and infinity, the image will be again on the left side, that is same size as the object, and it will be virtual, erect and diminished. Concave lenses are generally used in spectacles and in case of street lights. To solve the numerical problems, as we had a mirror formula, we also have a lens formula. F focal length, V image distance, and U is the object distance. But keep in mind that in the mirror formula it was 1 by V plus 1 by U, but in the lens formula it is 1 by V minus 1 by U. Why? Because in case of mirrors the light got reflected, but in case of lenses the light is being refracted and is moving, changing sides, therefore the sign is changed. The magnification also, it is Hi upon Ho, that is equal to V by U. Now in case of mirror we had Hi upon Ho is equal to minus V by U, but here it is plus V by U. Now comes the power of lens. The power denotes how much bending that lens is giving to the ray of light incident on it. If it is bending the incident light more, it will have more power, and if it is bending the incident light to a lesser degree, it will have less power. And the power is calculated as the reciprocal of focal length. But keep in mind that P equals 1 by F is used only when F is in meters. But if F is given in centimeters, you will use P equals 100 upon F. Both the cases, if the F is in meter, you will use this. If the focal length is centimeters, you will use this. In both the cases, the power will be the same. Now coming to total internal reflection. Whenever the light is traveling from a dense medium to a rare medium, if the light is traveling normally, there will be no bending of light, only the speed of the light will be changed. But whenever the light is traveling obliquely, it will follow the normal laws of refraction. For a certain angle of refraction, whenever the light is emerging out of water or any dense medium, when it is entering the rare medium, it will bend away from normal. If we increase the angle of incidence, the bending will be increased more and more until at a point, for a certain angle of incidence, the angle of refraction becomes 90 degrees. That is, now the refracted light is traveling along the boundary of the two media. That is called the critical angle. So critical angle is that particular angle of incidence when the light is traveling from a dense medium to a rare medium. That particular angle of incidence for which the angle of refraction becomes 90 degrees is called the critical angle. And if the angle of incidence is further increased from the critical angle, the light does not get refracted anymore, it will get reflected into the same medium. This is known as total internal reflection. This total internal reflection phenomenon is used in a retro reflector, a periscope, and the optical fiber. That brings us to the end of this chapter. Next, we'll be revising the chapter of human eye and the colorful world. Thank you.